Let us recall what we had said in the last class. We had actually constructed the Lagrangian of the semi definite programming problem SDP, and then we proved that if the following two assumptions 1 and 2 that you see on the screen, if these two are satisfied, that x hat is in Sn plus plus and kernel of A star is equal to 0, then if you take these two conditions, then what would you have is the following, that there would be a y bar element of minus Sn plus or a s bar element of Sn plus such that this thing holds. It is like a saddle bond conditions that you know in standard convex optimization, but we are looking at the whole thing from the perspective of SDP as a problem and trying to handle it. Now, what you have here is the following, then this would tell me that this is happening and this is what you get, where I am setting s bar equal to this. Now, then for this you apply the standard optimality condition for convex optimization and that would lead to these conditions. Now, is it the same s bar that you will give this difference? That is the whole question, or if this s bar is something else. The thing is that this s bar that you see here is an extra condition that we get when we study SDP. It is not that something which is associated with this. So, what we can show is that if you look at x bar and C minus A star y, then you would clearly see one thing, that this is nothing C x bar minus x bar into A star y, and by the definition of my adjoint, this is nothing but A x bar. So, these are matrices, so A x bar y. So, x bar is the matrix here. Here what you see is a multiplication between two matrices that has been converted into multiplication between vectors, inner product between vectors. Multiplication in higher dimension is inner product. So, this is nothing but C of x bar minus B of y. Now, if you observe what we have now, this because strong duality holds, because an x bar is the solution. So, C of x bar is minus B of y bar is greater than equal to 0. So, you will always, from the duality point of view, you always have this weak duality result. Okay. Now, what happens is the following, this is always true. Now, this is what you get. Now, C x bar is the primal one and B y bar is the dual one, right. Now, what I have to show is that this product is 0. So, if I write C minus A star y as some z element of Sn plus, basically my aim is to show x bar z bar is equal to 0. Now, what we have got, we know that the strong duality holds, that is C x bar the solution. So, this is greater than 0. So, C x bar minus P y would be equal to 0 if y is a solution of the dual. Right, because y is a solution of the dual, strong duality will give me this equal to 0, which you already have an idea of. So, I missed the bar sign here on y, it should be y bars here. This is just, I am sure you can figure out this mistake. Now, if I calculate theta of y bar, which is equal to mean of L x y bar, where x is element of Sn plus, then it implies that this is nothing that theta y bar is nothing but the value of SDP, and that is same as value of the dual of SDP, which is, and what is theta y bar? Theta y bar, value of dual of SDP, this is the value which will be nothing but By bar, that will be the value. So, theta y bar is value of SDP, value of dsdp. So, if the value of the dual problem would be given by By bar. So, in fact, you can prove that y bar is actually the value of SDP. So, if you look at theta y bar, what is the dual problem? It is maximize theta y bar over y bar element of Rm, right. Basically, the dual problem in our case, basically this is same as writing maximize, sorry, not theta y, C minus A star y is element of Sn plus and y is element of Rn. So, theta y, so the minimum of this is equal to By bar if this is true, but this is already true. So, I already know that C minus A star y bar from our previous result, this result, this is already element of Sn plus and theta y bar, which corresponds to the objective value of the dual variable, which is same as By bar, that is the theta y bar is the maximum dual objective value. The dual objective value theta y bar is actually nothing, is same as, has the same value as By bar. So, that is why By bar is equal to theta y bar and that is equal to 0. So, that that is why Cx bar minus By bar, this part is equal to 0, because what you have done, you have shown that y bar is dual feasible and theta y bar is actually the value of the dual. And what is theta y bar? Theta y bar is By bar if this holds true. So, if this is holding true, so theta y bar must be By bar. So, if this result holds true, if this fact holds true, then theta y bar is By bar, and we know already that this holds true. So, theta y bar is By bar, and we have proved very simply from the very basic fact here by using this fact that theta y bar again is nothing but the value of SDP, which by duality, because all the conditions of duality satisfied, is value of dsdp and this is this, and so this is equal to 0. So, what we now get is that if I put this equal to z bar, x bar z bar is equal to 0. So, my KKT conditions for SDP is as follows. So, I will have that if x bar is a solution of SDP, x bar is a solution of SDP if and only if, is a convex problem. So, it is an if and only if, you know this very well, KKT conditions are both necessary and sufficient. X bar is a solution of SDP if and only if there exists y bar element of Rm and z bar element of Sn plus such that, so such that A star y bar plus z is equal to C, A of x is equal to B and x z is equal to 0. But there is a very interesting result which says that if x and s, x and z, so you take any two matrices x and z, sorry z bar, So, this is a standard result. Since this is in Sn plus and this is in Sn plus, both are in Sn plus, then what would happen is the following. It would be like this, that this equal to 0 if and only if x bar z bar, this product is equal to 0. So, your KKT condition can now be framed for SDP, can be framed as the KKT conditions can now be framed as that if x bar is a solution of SDP, if and only if these exist such that S star y bar plus z bar minus c is equal to 0, a x bar minus b is equal to 0 and x bar z bar is equal to 0, where x bar is element of Sn plus and z bar is element of Sn plus. So, when you want to develop the interior point methods, the relaxed KKT condition that you use is the following. Is or takes a thing of this form. So, instead of 0 you put some mu into I. So, this is the relaxed KKT condition for the SDP problem, and doing something with this, trying to develop a Newton method for this can also lead to interior point methods for SDP, and IP methods for SDP exist when we will, and they are polynomial time, and we will try to discuss a bit towards the end of this our discussion, but we will not give too much stress to it. So, I am just showing a path by which you can do IP methods for SDP. There is a software called Sedumi for semi definite programming. So, there is a software which you can use and download it from the net and try to solve semi definite programming problems, may not be of very large scale, but quite standard scale you can do it. Now, before jumping into this bandwagon of what is, how can we really solve semi definite programming problems, it is it should be useful to know why semi definite programming is so exciting. It is not that because I just found that I can write linear programming in a semi definite programming problem, and for SDP I can write IP methods which are polynomial time, but we had also just discussed that for linear programming problem we can write methods which are polynomial time. So, it is not that SDP is the only relation between SDP's only use is maybe trying to solve linear programming problems. You see, we will talk about now the relation between integer programming and SDP. So, we will consider a very standard quadratic integer programming problem and xi for each I has to be either -1 or +1, there are two options. So, this is a very important class of problems called integer programming problem, where Q is a symmetric matrix. You could assume it to be positive semi definite also, it does not matter. Now, how do I Integer programmings are very difficult by its very nature, because if n is very large, then it is, one might say what is the problem, just you find out the variables which have this -1 or +1 values. That there are actually, if you take in 2 dimensions, then it is fine, you know, it is, there are 4 possible cases, and then you just figure out with the 4 possible cases what is the function value. But the question is, if I am talking about much higher dimensions and n is very large, so there are huge number of values and it is not possible to evaluate, the computer will heavily slow down if you want to make a direct enumeration. So, how do you solve such difficult problems? So, integer programming, if we could have solved discrete optimization problem, there would have been no study of optimization theory, and it wouldn't have been at all an exciting game. It is an exciting game because we know a lot about continuous programming, we will know about lot about continuous optimization, the things that we had discussed, where there was nothing, no discreteness of this nature in the feasible set. This discreteness is very important because this is practical. Practical problems demand discreteness, and so from the practice point of view, these integer programming problem or discrete optimization problems are very important. But how do we? But on the other hand, we have much better solution methods and very clear cut techniques or other technologies to solve convex continuous optimization problems. So, how can I convert this sort of problems into a continuous problem and try to solve them? So, one equivalent formulation in the continuous form is as follows. So, I am writing down an equivalent formulation which is given as follows, says minimize, you can put half x qx also, does not matter, subject to, here it was so I have now got n constraints, this is g1 x, g2 x, g3 x, but all of them are equality constraints. So, now I have converted this problem into a problem with a quadratic problem with quadratic equality constraints. Now, if I construct the Lagrangian of this function, let me just write down the problem again for your remembrance. So, I am having a problem of this sort, minimize this subject to. Now, what you do is, let us write down the Lagrangian of the problem which we already know how to write down. See, yi has no sign here because it is with equality constraints. This is my Lagrangian function. Now, I can write down the Lagrangian function in a much more compact way, is as following. So, Lxy can be written as, so this is my IP problem, integer programming problem. Where dy is the diagonal matrix now. If I want to find the dual of Lagrangian dual of this problem, what I have to do is to find theta y, which is to minimize Lxy over x element of Rn. Now, this minimum value, if you observe that if this is always greater than equal to 0, then this is greater than equal to 0. So, this is, if this is always greater than equal to 0 for every x, means this is positive semi definite. So, which means my dual problem, dual IP, is given as the problem of maximizing minus Ey subject to the linear matrix inequality. So, this is also semi-definite programming problem, because it is in the form of a dual of a SDP problem, and dual of a SDP problem is also an SDP problem. Dual of IP is an SDP problem. So, you see a very important class. So, now I can solve the dual, the SDP. There need not be, because it is a non-convex problem, then there need not be strong duality holding between these two, the original problem and the dual problem, but by solving the dual, which can be done by using techniques from semi-definite programming, we can immediately tell you what is the lower bound to the original integer programming problem. And in integer programming problem, in these sort of problems, we are actually looking for bounds. We are looking for lower bounds on the minimum value. We are not immediately wanting to find the exact solution. So, this is one very useful area where semi-definite programming can come in. In fact, if you write down the dual of this semi-definite programming problem, this problem as you take the dual of this problem, then you will see that it will look like exactly a semi-definite programming problem, and it will come in terms of the problem data. Where this vector E, I am not writing every time, E is this. So, here we see how a problem of quite high level difficulty as an integer programming problem can be approximated very fast in terms of a much more simpler and tractable problem, the semi-definite programming problem. So, this is something very important. There is a non-convex problem, you are actually formalizing it in such way that they become convex optimization problems. They become that you look it through the eye of a convex optimization problem. Even if you have taken Q to be PSD, that does not matter. Q PSD has no saying. Q to be PSD has no saying, because by the very simple fact that if Q is PSD does not matter, this ultimately this is a non-convex set. So, minimizing convex functions over a non-convex set is a non-convex optimization. So, non-convex optimization is being approximated fast, and some information can be generated about its solution by solving a convex optimization problem, which is in the form of an SDP problem, and that is why semi-definite programming problems are so important. This is actually called a semi-definite relaxation of the original problem. So, now you have a fairly nice idea of what a semi-definite programming problem is and how it could be useful. So, and I have already given you a hint how KKT conditions are developed and how they can be put into the framework used in the IP methods for solving linear programming problems. Now, because we are taking a tour of convex optimization, let us take a little bit of detour. So, what is this detour meaning? So, we will get into a slightly different stuff. So, we had been talking about linear programming, and SDP almost looks similar like it, all the functioning, but it is not. It is very powerful because it is a convex optimization problem, which you are almost talking as if you are doing a linear programming problem. So, we will get into slightly different stuff. In actual optimization, it is not always possible to get the minimum. For example, if I take a simple function from R to R, and it is a convex function, f x is equal to e to the power minus x. So, what is happening is that you see, if I take this function and if I just try to draw the graph of this function, this is x and this is your y axis, your f x. So, at 0 it is 1, so it is 0 1. Through this 0 1 point, this thing is coming and going down and down and down and down. it goes as near as possible to the x axis, but never touches the x axis. So, the infimum value of f is 0, that it is a lower bound or the greatest lower bound is 0, but there is no x in R for which so the minimum is not attained. Minimum or infimum in this case is not attained. So, what can we say of such situation? But if the infimum or the lower bound exists, if you give me any epsilon greater than 0, then there would exist, by definition, there would exist an x star such that f of x star is less than equal to inf of f, say over R n, if you do not mind, plus epsilon. If you change the epsilon, this x star will get changed. So, once I give the epsilon, you are always able to find this x star. So, any x star which is given an epsilon, which if it satisfies this property, it is called x star is called an epsilon minimum of f over R n. In real applications, we are essentially looking for epsilon minimum. We do not want to find the exact minimum, as we have seen in when we were studying the complexity of interior point methods for linear programming problem. We wanted to stop when the duality measure comes down below a threshold epsilon, we want to stop the algorithm. So, basically what you get is some sort of approximate solutions and not the solutions that not the exact one. In most cases you do not find exact solutions. So, now how to characterize such solutions? In case of convex functions, which we are interested in, there is a notion called epsilon subdifferential. We already have studied the notion of the subdifferential. Here we are looking at the notion of an epsilon subdifferential. The epsilon subdifferential, which we define as follows: at any point x naught is given as set of all xi in R n, or say let us just change it, so v in R n such that f x minus f x naught is bigger than v times x minus x naught minus epsilon for all x. Now, this del epsilon x naught is very important from the point of view of algorithms, important from computational viewpoint. So, what do I get? What do I get here is as follows. See here, even if this function is differentiable, it does not tell me that this epsilon subdifferential, which is convex set, it need not become a singleton. That is very, very important. So, if f from R n to R is convex and epsilon greater than 0 is given, to us, then x star is an epsilon minimum if and only if, which is usually used, this sign is used, if and only if 0 is belonging to, now very 0 is belonging to del f e x star. Now, one important thing to note that this function, this one del f e x star, so del e f e x naught in general, del epsilon f x naught is not equal to phi for all x naught in R n. So, this is a very important aspect of this subdifferential, that it is never empty, right. Now, okay, what would happen if my function is if it is differentiable? What, because I cannot say anything about the subdifferential about the epsilon subdifferential, that okay, it will be nothing but grad f x, grad f x naught. So, what can I say if the function is differentiable, if f is differentiable? This would lead us to the study of the Ekeland's variational principle. The Ekeland's variational principle, which is a far reaching result in the theory of optimization, is a very powerful one, and it tells us how an approximate solution actually behaves. So, we are now going to write down the Ekeland's variational principle and we will show how Ekeland's variational principle can be used. See, Ekeland's variational principle says the following. So, given epsilon greater than 0, suppose there exists x in R n such that f of x is less than inf plus epsilon, then for any lambda greater than 0, there exists y element of R n such that number 1. So, for any lambda strictly greater than 0, there exists y lambda y. So, y of course depends on lambda, which let me just write y depends on lambda. Such that norm of y minus x less than epsilon by lambda, number 2 f of y is less than equal to f of x, number 3 y is the minimizer of the function So, if I take this function, y is the minimizer of this function, that is the whole thing. So, this is something which is important and we should keep in mind. So, what it says that okay, let your function, original function need not have a minimum and it has a epsilon minimum, and let this be the epsilon minimum. Then I can find some epsilon another point near it, so that that point is a exact minima, rather a unique minima of a part-of function. So, this is my part-of function, this is exactly the part-of function. And this is my original function. Now, if f is convex and x star is an epsilon minimum, what can I say? That and assume f is differentiable. So, tomorrow we are going to compute these facts and we are going to show what happens if we take this question. A very interesting fact will emerge and you will see that even if the function does not have a exact minima and if the convex function is differentiable, we can tell a lot about the characterization of its inexact minima. So, basically we are having an inexact minima or epsilon minima and we are finding another epsilon minima, right, because if this is true then I can put this is less than f y. So, y is also an epsilon minima, which is a unique minimizer of some other function. So, this part-of function plays a fundamental role in this story. So, I would just like you to take a look at this very carefully, because this is a very important result and it is very important to, it is of great importance to know this result if you are going to study optimization theory, because in actual practice you are going to look at only epsilon minimizers, you are not going to look at true minimizers. So, tomorrow we are going to discuss, starting up from here, what happens when x star is epsilon minima and what can I say that if it is f is further differentiable. And for that you would have to know a very important result, which says if you take the norm function and find the derivative at 0, this is nothing but the unit ball, that is the ball of radius 1 centered at 0, and this fact would be used in tomorrow's, we have to use it here in tomorrow's discussion. Thank you.